but let's make sure. Okay, now we are recording, which we need to, except now I'm going to pause the recording. Okay, we are back to the recording. Sorry, we missed all the hellos in the recording. I'm sure that's fine. Um, but hello, Genesis, and hello, Norma. Okay, so yes, I apologize. Thank you for correcting me that we didn't have class Monday. Okay, now that means that in principle we do have class Friday, which is awkward because for many, I know that causes problems for people that have jobs and things. And actually, it causes trickiness for me too. For the moment, let's assume that we are doing class Friday as we're supposed to, because I would like you to have that time, you know, I was counting on two classes this week since your exam, as you know, will be posted Friday evening. So assume that you will come to class Friday and that by that point, really, it would be greatly to your benefit, if not earlier, to have looked through this practice exam document and come with super specific questions about the practice exam document, and which I'm going to start addressing today anyway, but I hope that's sort of clear that and if you can't come to class, I understand that, but then like watch the video. I think there's something in the chat already. No, there's not. Okay. So, because, right, in principle, as of now, and I hope this is clear, tell me if this is not. My understanding is that you're going to have an exam that will be posted by no later than 8 p.m. Friday evening, and then you're going to turn back to me no later than 9:25 a.m. next Wednesday. Right. First of all, that is you. Just raise your electronic hand if that is your understanding or if you're like aware of that. Okay. Thank you, Mohammed. Caught that. Okay. Oh, see. Okay. Thank you, Nadine. Thank you, Gabriella. Okay. Thank you, Sydney and Ziva. Okay. All right. So now, and again, I don't want to get, um, like, I want you to be as prepared as possible. This is the first, this is your midterm exam. Then you're going to have a final exam. Then you're going to have two more like this in Physics 204, hoping that you all stay with me, you know, and so it's a thing to get used to. Like it's always the same way that I do exams, or that we do exams, well, that I do exams. And it's a little, the first midterm in 203 can be jostling, can be a weird experience for people. I don't want it to be. Um, um, but let me emphasize again that well, you should watch the video. There's another video where like I'm wearing a hat and like some weird like colorful vest or something like thing. You should watch that as an overview of like what's expected in this exam of like how to do it. As far as what the material is, that the exam from last semester or 2 semesters ago that's in the Google Classroom is your best guide. I don't publish solutions to that because I'm giving you that so early in advance. And because the actual exam will look so similar to that, it will be shorter. You should know how to do every single problem in that practice exam. You should, but know that by the time you get your actual thing, it'll be like a subset of that, or you'll get choices or something. So you won't do something as long as that. And you won't do anything on your exam that isn't in that. I hope you get the point. But like that's the thing to know before you get to Friday night. And again, just to be clear, since we've never done this before yet as a group, once the exam starts, like once it gets the actual exam gets posted Friday night, you can and should do anything you want in any way you want. You can work with one another, believe it or not. You can go on the web. You can use ChatGPT and all that stuff to figure things out. I'm not stopping any of that. In fact, I mean, like, and you should know that your colleagues will be doing that and that I know that they'll be doing that. So you might as well take your time and all that, but then you got to know the hook of the whole thing. Oh, sorry, there's a question. I'll get you in one second. All right, I'll stop in a second. But the overview is that therefore you really want to look at this exam. It's not like an exam. It's not like a test of what do you remember or what answers do you get correct? Because we'll all know that we all have access to all of this material all over the world and all over what it is, what you're giving me at the end is a presentation. I mean, a written presentation. You're giving me as clear and as comprehensive and as extensive a final copy of your full 5-step method walkthrough of the solutions to all these problems. You're trying to show me that at the end of the day, after you used every resource possible, every old video that I've ever posted on this material, which you're welcome to do, where I do walk through solutions, by the way, you could find any solutions you want and share them with one another. But then at the end of the day, you're writing a big document that shows you understand in what is going on, which means at any moment, whenever there's a doubting mind, if you're like, does he really want me to show, like now I divided both sides by 2. Does he really want me to show that? Like divide both sides by 2? Yes. If it even occurs in your mind to say, should I show this step? Like, should I explain this? Yes. The more you explain, the more you do different colors, the more, I'll shut up in a second, but the more you have things in the margin, more diagrams you have, the more you can, you're trying to teach me the material. Think of it that way if you like. And you're trying to give it to me in a way where I don't, a self-sufficient document. I don't have to look at the test myself. I don't have to look at the questions. I don't have to look at anything. Or if I got sick and I gave it to another physics professor, as long as they know physics, they don't have to look at anything. They would just look at your document and be like, oh, this is what she's trying to solve. Oh, this is the setup. Oh, this is what she's doing. Oh, this is her solution or him. Like what, like, oh, I get it. Like everything is just self-contained physics from start to finish. And you're really showing me that you really get it. Like that's your goal. Okay. Okay. And so I'm going to, so I'm going to try to talk about it like now in a minute. But first of all, there's at least, I think there was a question, or I just saw a hand, or maybe that was still, was that a question? I saw a hand, or was it just a affirmation that you knew what I was talking? No? Okay. Okay. I will say I did, if every one of you did the asynchronous thing where you wrote questions that where you were like, this is what I understood in the videos and this is what I didn't. I didn't put comments because I was trying to go fast, but I did read them all. So I know, so those kind of questions you can repeat today if you feel like it doesn't get answered by today or on Friday. Um, um, but what I'm going to say today bears many of them in mind. Um, um, so what I want to do now, okay, so I want to start trying to help you with the material that's in this practice document. Like some of it you've already done, some of it you haven't. A quick question though, sorry, on this topic. I always forget. You have Professor Lou for lab, correct? Yeah, okay, thank you. I saw that, Mohammed. Thank you, Nadine. Thank you. So tell me, and your lab period is Friday? Right. Okay. And that's why I'm put, but it ends before. So, okay. Has she mentioned to you, do you know what you're doing in labs this Friday? No.
We
Okay.
don't have lab on Friday.
Oh, right. What am I saying? Because, right. Of course. Of course. Right. 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 Okay. And what did you, and in lab last Friday, you did a board meeting, correct? Okay. And by the way, Will, I don't want to get rabbit hole about this, just for the record. I don't know how you felt about it or whatever. What I know is this, while people do board meetings, often students can feel very frustrated and feel like this isn't going anywhere. This isn't going forward. I don't understand this. I just feel like we're going backwards or this is disorganized. It often feels that way. And I'm not going to argue you out of that feeling. What I do want to say is a board meeting experience, as frustrating as it can often be one of the most valuable experiences to have right near an exam or right before an exam. Because the real point of a board meeting experience, in a way, is not to cover material, but to uncover material and discover. It's really meant to. It's designed. I'm not saying it always goes this way or always feels this way, but it's meant to show everybody where they don't understand things, what they need to think about more in their own way. So hopefully maybe so if you felt like, oh my God, I feel like I know even less than I did when I was coming into this board meeting, which sometimes people do, that actually means you kicked up a lot of stuff just in time before this exam. So I definitely encourage you guys. I hope you guys have a WhatsApp group or like a Discord server or blah, 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 blah. And I hope you guys get together over the next couple of days, even electronically. And even once the exam is posted, I encourage you to help each other with this stuff. But just know that, and I encourage you, the best way you could do this exam would be to do a rough draft first, like with other people and things, but then give yourself time before Wednesday morning to go back to your own apartment, your own room, and actually then sit down with everything you have and write it a final copy that's super clear, super inviting, that I super want to go through. The more extensive and the more explanatory, the better. Okay. You don't have lab, right? Sorry. Thank you, Teresa. Sorry. Okay. Here's what, so now what I'm going to go right now straight to what I think is one of the harder problems in the practice exam, the one that would look the most unfamiliar to you or the scariest to you, possibly, I would think. I'm going to go to it right now and try to help you with it. Kind of on the assumption that some of the, or okay, in fact, actually, hold on. I'm going to switch screens. And I'm going to do more of what I'm about to do right now. I'm going to do more of this on Friday for you, but it would be even better if you have questions, really specific questions that day. Okay, but so like here's the practice exam, right? Again, this is what your exam will look like. You'll be given these equations. And these equations, if it's on the equation sheet, wait, I'm looking. Yes, this is a good equation. If it's if it's on the equation sheet, particularly those equations 1 through 9 that aren't written off the side like that, I would consider those step 3 GDPs. Like, and again, to reinforce, you absolutely want to do the 5-step method on this exam wherever possible. Like, occasionally questions don't lend themselves, but wherever possible, you do the 5-step exam, 5-step process. You label your steps, like literally say, here's my step 1, here's my step 2. And even if you think with step 1, like you've already done the diagram 50 times, even if you're saying see above, see page 2, fine. But just like acknowledge every step. And I'll tell you right now that was particularly when I'm grading exams, what I'm really looking for in a way, a lot of the thought and the personal nature of understanding comes into step 3. Like step 3 is where you kind of have to think. And then once you establish step 3 correctly, step 4 is a crank that starts turning. This equation sheet is where you want to, that's where you find legitimate step 3s for the most part. I would also, I would say that the two that are off in the side like that, the two equations are off in the side, at least the first time you use either one, I would highly recommend that you explain it and show where that it came from the others, like we did in class. You don't have to do that every time, but like the first time you introduce something new, break it down and show. I also want to say Galileo's principle of relativity absolutely counts as a step 3 GDP. Like you can't break that down any further. It's a principle behind the laws. So anything we've ever said about Galileo's principle of relativity, you should think about and consider as a step 3 for many problems. And I'm going to give you, and so far we have 4 forms of Galileo's principle of relativity, but I'm going to give you another one today that looks much more mathematical than all the rest. It absolutely counts as a step 3 GDP. It probably almost should be on this sheet, but it just happens not to be. Okay, then you'll notice you get choices. Your choices won't be the same. You'll get some kind of choice. Your exam will not be a 5-hour exam. All right, these are exercises. I'm not going to go over these now. I feel like, whether I put them on your exam or not, I feel like we've covered this stuff a lot. This exam, I mean, sorry, this problem, I hope you can see, I'm going a little bit fast, sorry, but you can see on the screen, right? Yeah. This thing right here, 2 1D simultaneously independently, if you look at this in your own time, or if you have already, what I want you to notice is that this problem, it seems like out of nowhere, it's like whatever, it's cartoon characters. This is the big old duck, just like turned on its head. It is the big old duck. And you've now been assigned a video and I got all your responses. Like some of you had really good questions about the big old duck, but it really does seem like you paid attention and you figured out some things that you didn't know before. So, and there are walkthroughs of this again all over the channel, but But specifically, if you're trying to understand how this problem works, understand the big old duck problem. And the bottom line behind the big old duck, I'm going to move on in a second, but the bottom line behind the big old duck is it is itself is lab four, right? Lab, if you see at some point in your mind that lab, if you see the relationship between lab four, I think it's lab four, yeah, with the marble going off the table, right? Lab four, um, big old duck, and this, if you see other, then you really see something. And what is it that you see? You see that these are all two-dimensional problems that really just ask you to do two separate one-dimensional problems, one at a time, but link them together by the time, right? So this one, just like the meat of this problem is part D, where it says how high was the cliff. That's like the biggest, the bulk of the work of the problem. That's the main show. Just like in Big Old Duck, the main issue is like how far back was the duck placed? And the way to do this is just like that. First in this problem, and I'm going to go on a second, but first you look at the horizontal axis and do physics to figure out how much time would it take for the roadrunner to get from where she is to the same horizontal place as the coyote. Like, I'm going to say that slower. Like in lab four and in the big old duck, you first look at the y-axis to figure out how much time would it take for something to go down this height or go up this height. In this case, it's just turned around so that the facts, so that you look at the x-axis first to figure out how much time will this motion along the x-axis take. And then you use that time to plug in to the y-axis and solve for how high the cliff is. Okay, that's how you do this. And just like the big old duck, you're going to get two answers for this, for question D. I'm going to slow down and pause for a second. And definitely, I'm just trying to get to stuff, but you can slow me down too if I'm going too fast. But I'm going to pause here because this is where I got a couple of questions, really good questions from you guys about the big old duck video. Okay, so number one question that people asked is, hang on, is it okay to assume from now on, like they gathered from the big old duck video, people asked, wait, does that mean like from now on, anytime something is just like going straight up or straight down, can we always use that 9.8 number as acceleration? Good question. Answer, yes. You might want to write this down. It's hard for me to, because I'm doing two screens at once, but here, the definition of free fall, the definition of free fall is an object that has an object near the surface of the earth that has no influence on it, no force on it, no influence on it at all besides gravity. That's what free fall is. In other words, an object when nothing is touching an object at all, where an object is just being pulled down toward the surface of the earth, and that's the only pull or push on it. That's what free fall is. And whenever an object, I'll say that one more time. Free fall means no push, pull, or touch on an object other than the pull, the gravitational pull of planet Earth. That's what free fall means. And as long as something is in free fall, yes, you can assume that it has a constant acceleration of approximately 9.81 meters per second squared, pointing along the vertical axis. Like something in free fall has a vertical acceleration that is constant of approximately 9.81 meters per second squared. So yes, like that's really sort of the point of lab 2, actually. But yes, that's true. I want to lean into that for a second too. Like, yes, you can rely on that. if if you're if you're in an exam, if something comes up on an exam where something's like falling or going up or whatever, yes, you can rely on that number. But if it's an exam, if you're not in a lab, wherever possible, or unless you're told otherwise, you can round that number to 10. And I encourage you to do so. Definitely on this exam. Any place that you would think that you're going to be using that number 9.8, you can round it to 10 meters per second squared. That's a good thing. It'll make your life easier. It's what physicists do. That's number one. Number two, just note conceptually that that's an acceleration that only applies to the vertical axis. That's kind of the purpose of this problem and of lab 4 and of big old duck, is to realize, yes, anything in free fall, I mean, even if the thing is moving up, even if the thing is moving in an arc, as long as nothing is touching it at all, then on the vertical axis it has an acceleration of 9.8, but not on any other axis. Okay. Lastly, I should be writing these things down, but I'm trying to screen share. Lastly, no, because someone else asked this too. It's pointing down, the acceleration due to free fall. The acceleration is pointing down. You could be moving up, but the acceleration is still pointing down. That means in English, if you're falling down, you're gaining speed. If you're moving up, you're losing speed. Do you call that positive or negative? That is your choice. At the beginning of a problem, in step one of every problem, like on this exam or in life, step one is like diagram fact pattern. Part of that is making a coordinate system. This particular problem, oh God, sorry, there's things in the chat. I'll shut up in a second and look in the chat. But this particular problem actually asks you to sort of label things positive and negative. Problems don't always ask you to do that, but you always need to do that. And what I'm telling you is, it's up to you to decide whether down is positive or negative. And that will determine whether the 9.8 number is positive or negative. You make a decision and then you just stay consistent with it. My recommendation is that you want as few negative signs as possible. So if something is only going down and it's never going to go up, you might as well make down the positive direction. But if you have a feeling that more than one direction is going to be involved, then sure, make up positive and down negative. I'm going to pause because there's things in the chat. Sorry. And then I'm going to move on with this. Hold on. Oh, sorry. Okay. So some of these. Okay, right. So something in the direct chat. Yes, we are neglecting air resistance. That's right. We are not. I'm not saying physics cannot handle air resistance, and I'm not saying that gravity includes the concept of air resistance. But yes, I am. We are assuming right now that the air resistance effect is small enough not to affect our numbers. That's about like that these objects are heavy enough or non-aerodynamic enough, not like we're not dropping feathers, we're dropping marbles and whatnot. So yes, we are neglecting air resistance. We're treating it as small enough not to affect our numbers. Later on in physics, we can deal with it directly. I mean, but we're neglecting it. Just like so I don't mean to say that gravity is factoring that in. It is a different factor, but we're just saying right now we're treating objects where the factor is too small to matter. But good question. Then there's another question in the chat. Wait. Oh, yes, great. Yes. So I'm saying this is the vertical acceleration for this problem that's on your screen right now. You you can assume the vertical acceleration is 9.8, which really in the exam I would make 10 if I were you. That is not just permission, that is an encouragement. It'll make your numbers work out better. It'll make me have an easier time following your numbers. It is what physicists do. And don't think you're lying when you do that. You're not lying. 9.8 is an approximation in the first place. You're just approximating more conveniently. But whether you make it negative or positive is a choice you have to be conscious of. And the last thing about the positive and negative, because this also came up in one of your questions about big old duck video, like say you call down negative. So now you're saying acceleration due to gravity is negative 9.8. Okay, fine. That's a customary choice. That's fine. That means that the acceleration is negative 9.8, period. It means it's constant. It means whether an object is now velocitizing up or velocitizing down, still the acceleration will be negative both ways. The acceleration doesn't change its sign. That's what it means to say constant acceleration. The velocity will change its sign because of the acceleration, but the acceleration does not. Just no, so that came up. All right, I'm gonna move on in a second, but okay, I think that's the chat for now. But keep the chat coming. It's good, and it keeps me on task. But I also want to remember there was another question that another big question that people asked about the big old duck. Oh, yeah. Now I'm going to say this quickly again because there's so many videos on it, and I don't like want to waste your time. People, a number of people that wrote me the questions about the big old duck video, a number of people were confused about why two answers. Okay, and that's an important thing. Like that is not easy, but it is super important to the problem. And it will happen here as well. That you're going to get two, like in this exam problem here, it asks D, the central question, how high was the cliff? Show all work. And honestly, there should have been point value. Like that, I don't know why they aren't in this document, but you should understand that that question would be worth a lot more of the points than many of the ones before it. And it would be clear in your exam. It'll say the point values. And again, remember, you're getting points for every step that you do. Like, and you're losing points for any step that you don't have, even if your answer is right. Whatever. I think I've made that clear. So this is a central question, D, how high was the cliff? And yeah, I'm asserting right now that if you do this problem correctly on the exam, you're actually going to get two different possible answers. The cliff could be so high, or the cliff could be at another height, I believe. Wait, am I right? Hold on, let me just see. Yes, yes. And that's for the same reason that in the big old duck, it asks where would the duck be placed such that, when the duck arrives here, it gets shot by the bullet. And there's two answers to that too, and they're both just as correct as the other. So why? Well, the answer, why are there two? Because in both cases, I'll start with the big old duck. You fire a gun and the person fires a thing, a ballistic, and the first thing you're trying to solve in big old duck is how much time would it take the bullet to get to a particular height, right? The height that the duck is. Well, the thing is, you're firing a bullet up against gravity, right? So the bullet has an initial velocity that's, say, positive, but it has an acceleration that's negative. So that necessarily means that that bullet is going to be slowing down, slowing down, slowing down, slowing down, reaching a peak height, and then continuing to lose. It's like losing velocity, losing velocity, losing velocity, then gets to a peak height and continues to lose velocity because acceleration is constant. So it gets to a velocity of zero, but then continues to lose velocity. So what does that mean? It means the velocities now become negative, right? So they become increasingly large negative numbers, right? So now it's coming back down, speeding up, speeding up, speeding up, right? In other words, I'm saying what goes up must come down, right? So what? Well, that means that as far as the math is concerned, when you ask the math and the physics, when you ask at what time will the bullet be at this particular height, given an initial velocity that's positive and a constant acceleration that's negative, if you ask at what time will the bullet be at this height, there's two possible times, one on the way up and one on the way down. They are both times that the bullet would be at that height, right? Physically, one's up, the other's down. Mathematically, the way to get those times is you're solving for t in a quadratic equation. Like you're right, y equals 1/2 at squared plus v naught t. And v naught is not zero. I know, again, I'm speaking fast. So, I mean, this is like technically like review exam prep. So stop me if any of this doesn't make sense. But it seems to me mathematically, you're solving for t in an equation that has a t squared and a t in it. Hopefully the equation factored. I think it did in the homework, but even if it didn't factor, you would do the quadratic formula or something that, or you'd have a graphing calculator. But you're going to get two roots to that equation, and they both physically make sense. One is when the object is on its way up, the other is on its way down. And so then you take both of those times. I'm talking big old duck now. You take both of those times and you plug into the horizontal equation that you have a duck that has a certain acceleration and a certain, velocity, and you solve for each one of those times. And it means there's two options. Like the duck could be here in order to be, it could be close by so that it just gets there right when the bullet is on its way up. Or it could be all the way back here so that it's moving, moving, moving. The bullet has time to go up and then come down and slam into the duck, right? Like there literally are two answers that both mathematically and physically mean something. And same thing here. Here, and then I'll shut up or I'll look in the, oh, there's not anything in the chat, but okay, that almost concerns me. But okay, here, it's the other way around. Like the road runner is moving, the road runner is moving east down below, is moving east, but has an acceleration pointing to the west. So that means the road runner is necessarily slowing down while going, but it says constant acceleration. So that means when the road runner gets to velocity zero, according to this problem, she continues to lose velocity. So she now goes back the other way. In other words, she's doing horizontally something that's equivalent to what a free fall up and down thing would be. So there'll be two times here as well where the roadrunner is like directly underneath the falling object. So you'll get two answers. I'm gonna go on a second, but that was meant to be what I just said. Some of you already knew, like if you're like, wait, I already did the homework, I already knew. Right, but many of you asked that about the video, and and since it was just a video, since it wasn't me talking, I want to make sure that's clear. So that's the issue in this problem too. I feel like, wait, it's 10:00, we still have 40 minutes. Right now I'm just like walking you through the practice exam so you know how to approach it. What I'd like to, um, oh, okay, there's something in the chat. Thank goodness. Okay, hold on. Okay. For the duck, this is direct chat, so I'm not going to read the person's name, but it seems like a relevant question. For the duck, wait. Oh, okay, this is interesting. I'm not sure I told. All right, so the person's putting in the chat. The person says in the chat, since one of the distances was negative, one of the displacements was negative, and the duck hadn't turned and traveled the other direction, wouldn't the bullet only hit the duck on the way up, not down? So I, so I, so the person's saying, I think like it's true that the duck doesn't turn around, at least not in the main part of the big old duck problem. The duck does not turn around. I agree with that. But the bullet does. So I think what might be confusing about what I'm saying, or where we might be having a disjoint, is I'm not, wait, to everybody, I am not in the big old duck problem, which is this. I'm not saying the duck is going to be hit twice. There's no way the duck can be hit twice. I totally agree with that. I'm not saying the duck is going to be hit first when the bullet's on the way up and then when it's on the way down or anything like that. I'm saying since there's two options as to when the bullet would arrive at a certain height, then there's two options. And since what we're trying to do, we're just trying to plan an intersection between bullet and duck. We're trying to set things up so that the bullet and the duck are at the same place at the same time. And what I'm asserting is since there's two times that the bullet will be at that place, and our whole goal is like where to put the duck so that it gets there, I'm saying there's two options. You could put the duck close so that it goes and goes and goes and just hits the bullet like early on, like right when the bullet's on its way up. Or you could put the duck all the way back here so that it's going, 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 and the bullet gets to that spot, but the duck isn't there yet. But then the duck, so it's like, oh, damn, I missed. But then the bullet keeps going up and the duck keeps going. And then just when the bullet comes back down to that spot, then the duck arrives. In other words, I'm not saying it's both. I'm saying it's one or the other. And I agree with you, direct chat person. I don't think the duck is turning around, but I feel like the mere fact that the bullet turns around means there's two options. I don't know. And one other way I'll say, and maybe tell me in the direct chat whether you buy that or not, or we could talk later or whatever. But the other thing, what I'm really saying to everybody is, if the quadratic equation, if the math seems to be spitting out two answers, then as a physicist, anytime we get to, even if one of the two answers that's given by the math doesn't at first seem like, even if it feels like we were only thought we were looking for one answer, if the math gives two answers, we at least have to think about both of them. They mean something. Sometimes one of them might not be what we're looking for, but they're not, it's not an accident if they both come out of that. So I don't know if that answers the question or not. You'll let me know. Um, okay, it does. Oh, great. Thank you. Okay, thank you. And submit for tons of points for that. Okay, awesome. Oh, okay. Oh, wait, oh. Ooh. Now, good follow-up question from a different person, Nadine. If time is negative, we neglect it, right? Okay, that's a really good. Okay. It's a really thoughtful question. Uh, my answer is if you're doing stuff, especially in an exam, assuming that there's no, if you get a negative answer for time, um, you shouldn't neglect it. The first thing you should do is think about, wait, am I sure I didn't make a mistake? I'm not saying you did. But because you're right, something is funny about negative time. So if you ever get a negative, see, this is the thing in general, all of you with the exam, these are great questions. You want to be very careful about your positives and negatives. Like that's why we start, like they mean direction. So you first always choose positive means to the right uh, on this axis or something, and positive means up on the other axis, or you make a different choice. But you make a deliberate choice for each axis, what positive means and what negative means, and you stick to that. And with all your velocities and accelerations, everything that you plug in, you ask yourself always, like, should it be positive or negative? And you, like that's like a thing in physics. Then, if you at the end of the day get a time answer that's negative, oh yes, it should give you pause. Oh yes, you should say, oh, that's unexpected. So the first thing you should do is see whether maybe you made a mistake somewhere. Like it means something. First, you should see, but then maybe you didn't make a mistake somewhere, but but then ask yourself, but what could it mean? I mean, yes, if you have two answers for time and one of them is negative, I definitely agree with Nadine. I think it's a great observation. If there's two answers being spat out for time and you weren't expecting two answers physically, and one of them is negative, oh yeah, probably the positive of the one is the one you're going to use for the rest of the physics. That's probably true. But to be super honest, you don't ever just want to throw the negative one away and say, oh, that's like enough. That's just like weird math. Forget that. I'm moving on. It always means something. And the more you can see what it means and tell me in the exam, the more you're doing good physics and getting a good grade and all that. Because I'll give you a really quick, in the lab four, for example, in the lab four, yeah, if you in lab four, when you solve for the time that the bullet takes to go from the table to the floor, if you really solve for that time carefully, I mean, even that equation is a quadratic, and technically there's two roots to that. And one of them would have been negative. It's true. I mean, it's a really good example. And most of us just like threw it out, didn't even think about it. Like, whatever, oh, negative, obviously that's stupid. But even there, it meant something. What that was if the acceleration stayed constant as you plugged in, like the truth of the matter is the ball would hit the ground 1.2 seconds like after the bullet was shot, but also if that was one long continuous arc with acceleration forever as the math believes it to be, the ball should have also been at the floor 1.2 seconds before it was shot. Like if I don't want to get bogged down in this, but what I'm saying is the negative always actually means something. It does mean something. It just often might not mean anything that you're interested in that moment. But the more you can explain on the exam, if you get a negative thing, explain what you think it means or why you're throwing it out and not using it. Okay, that was kind of a long, but yes, in general, negative, but first check that you didn't make a mistake because there's no accidents in math, if that makes okay. But great question, great question. Okay, okay. This problem here is a great problem. I'm not going to talk about it right now. Ideally, I will either talk about it Friday or you'll ask me questions about it. But there are tons of videos that I made about this. Okay. But the whole I'll give you the fast hint about this problem. You'll do it on your own time, do it with each other, watch the videos and stuff. The purpose of this problem is it seems really hard. Like you're trying to figure out how fast the water is going past the shore based on a bunch of facts that you're giving. And if you just do it by conventional, like if you just try to memorize a bunch of equations and put them together, you can get an answer, but it takes a ton of work and it's really confusing. And oh, and this is a classic. I'm going to tell you right now, you put this into ChatGPT, and I'm not saying this as a, I'm, if you put this into ChatGPT, it will give you a solution or Gemma, whatever. It will give you a solution, and the answer will be right. But it is so hard to follow and so complicated and so beyond the scope of anything that we ever talk about in this class that first of all, it's totally obvious. Anybody who puts this into chat, just so you know, it's super obvious when people put this problem into chat or some version of it. But second of all, the purpose of it is that if you really follow the principle of relativity from Galileo, that I'm going to try to re-emphasize again for the next half hour, this is a classic case where if you see that there's a conceptual thread to this class that isn't just about raw equations, if you really believe that the laws of physics are the same at all unaccelerated in all unaccelerated perspectives, then you can solve this problem really easily, really quickly and concisely with very few equations, and you can get an answer. And I'll probably summarize that on Friday in the videos. But the test of this problem, especially if it's a choice, I don't remember. Like say you have choices and you choose to do this problem. I'm telling you right now that there's not a lot of computations to do if you want to do it correctly. But what there is key things to explain where you came up with those equations. And that's what I look for in this problem is you to show me that you understand how to do this really simply using Galileo's principle of relativity. And I'll give you the hint right now. I'll even say it. If, like pro tip, if you want to write this down, the hint for this problem is analyze the problem from the perspective of the water. Like there's a bottle in the water that's like floating. Okay, you'll read it on your own, but there's a bottle that's floating in the water and it floats for a mile before it floats for 20 minutes before the boat realizes that it's dropped out of the bottle. And so then the boat turns around to go catch up to the bottle and it finds a bottle a mile down below the bridge. If you take the facts of the problem and analyze them and observe them from the perspective of the water, as opposed to the perspective of the land, so you do the non-obvious but physics correct thing of like, what would this all look like from the perspective of the bottle? If you do that, it makes the problem much, much easier. It is the trick of the problem. And I'll even give you another pro tip. The key insight is that if you look at the problem from the perspective of the bottle, which is in the water, you'll see from the bottle's perspective, like a boat goes away from it, like from a boat, like is going up away from the bottle, and the boat reaches a certain place, and then the boat turns around and comes back to the bottle, right? As opposed to if you're on the whatever you could if you're the bottle, you see a boat go away from you, and then a boat come back to you. Now, if you watch from the perspective of the shore, you'd see a boat go like this, go up and then go down much, much further, right? If you even look at this picture, there's a boat that goes from a bridge, goes up, and then realizes it dropped a bottle. So then it starts going back down the river, passes the bridge, and catches up with the bottle way below. So from the perspective of the land, you would see a boat go up a little ways and then come down a long ways. But if you watch from the perspective of the bottle, a boat goes away from you and then comes back to you. So from the perspective of the bottle, the boat goes a certain distance away and then comes back that certain distance, all the while a land and a bridge are all moving past you. So if you do it from the perspective of the bottle, the boat goes up the same distance as it comes down, not from the perspective of the shore, but from the perspective of the bottle. I'm telling you right now, obviously go home and think about this. I'm not like solving the whole thing for you, but I'm telling you right now, if you go home and think about that, you'll realize that that's what makes the problem really easy to do from the like that is more information that you're getting if you look at it from the perspective of the bottle. And and the point of physics is that the bottle's perspective is no less or more correct than the land's perspective or the sun's perspective or Jupiter's perspective. So, from the perspective of the bottle, the boat goes up the same distance as it comes down. And that's the insight. If you choose this problem, if you do this, but like study it at home, work with other people. But once you get that, that is the thing that you would explain to me on the exam. I mean, that's my pro tip right there. That when I ever grade these problems from people, what I'm looking for is do they just take for granted that the up trip is the same as the down trip, or do they explain that the up trip is the same as the down trip if and only if we're looking at this from the perspective of the bottle? That's the hook. So it's more of a concept. Okay, I'll move on, but that's you'll understand it more when you look at it. I think I hope. But that's the deal with that problem. Um Now finally, it's 10:15. Okay. Finally, yes, this I think is the thickest, hardest problem of the exam. This is what I'm going to now get into more detail about. Like this is what you haven't really seen with me yet, but we still have today and Friday to talk about. Um So what this problem is about, and the and if you and by the way, this problem here is what you were doing with Professor Liu in the board meeting, more or less. Like this is actually an easier version of what you were doing with her in the board meeting last Friday. So I think the bulk of where you would want me to spend my time with you over again, Friday come in with questions, but mainly what I'm going to focus on today and Friday for the rest of today and Friday is this right here. I think it's the meat of the exam and specifically, and then I see something's in the chat. That's great. Specifically, your goal here, the where the most points really are is like part D. I mean, okay, like so if you can really conquer or understand how to do part D by Friday night, I think that's a good goal. Let me look at the chat. Hold on. Oh, wait. Good question in the chat. It says, when I say that you have to explain your answers in depth, is that in step five? That's a good question, but no. I mean, it's a good question. By step five, so again, that reinforces to everybody, if you're just tuning in out, like you are definitely doing the five-step method on this exam. You're overdoing it, in fact. Okay. You've been practicing the five-step method in homeworks as like the skeleton for how to do an exam. It's the skeleton. It's the minimum. And it's how I grade. It's what I'm looking for, is all the steps. But you want to use that as a skeleton to go crazy. You're going to put all the skin and bone, I mean, all the muscles and skin and everything on that skeleton with all of your with over exp when in doubt you're going to over explain. And so my answer to this person's direct chat question is by the time you get to step five, no, that's just the answer circled. You're explaining a lot all the way until you get there. I would say, as a rule of thumb, the longest step, usually, like really where you're really explaining things in more than one way, maybe using please using different colors, putting things in the equations in the center, and then putting English commentary over to the margin. Like that would mostly be in step four, usually some degree in step three, but the bulk of a problem is like the transition from step three to step four. Like that's really where you're strutting your stuff, to answer that person's question. And again, I just cannot emphasize enough. You want to view this exam as like a presentation. I mean, a written presentation, but it's a presentation and you want it to be neat and presentation counts, like matters. You want me to want to go through it and look at it. You want it to look pretty, like honestly, or and some people obviously are, I'm a but so if you have to type it, you have to type whatever. But I really am saying that when you're always explaining things and it's mostly in step, from step three to step four. Also, when I say explain, that means a combination of equations in English. But honestly, like, yes, you're using the equations, but you have the equations and they're all over the web and stuff. Really, when in doubt, you're going English. The more English or whatever your language is, like the more, well, I don't know that many languages, so it kind of has to be. But the more you can give English and drawings, you're showing me that you get it. You're not spitting back to me just correct physics. Like I already know correct physics. So a lot of people struggle with this, especially on the first exam. Like if you think you understand something, then that means you're thinking of it your way, not my way, your way. So communicate that. And I'll just leave it at that. But English is good. A lot of times people think, well, I don't know how to explain this. It's just like it's because the velocity is bigger, and so that thing is small. So right. So say that. This is an essay as much as anything else. All right, I'll stop. But I think you get the point. Hopefully you get the point. All right, we have 20 minutes. I'm going to switch the screen share now. I'm about to address. I'm not doing this like point for point. There's videos on it, but I'm giving you how to approach this problem here that's on the screen. So now I'm going to go, to the other screen. So bear with me for a second. Okay. Well, the purpose. This is what I want to show you right now. You could write this down. This right here on the board is is how you do that problem. And this is Galileo's principle of relativity, form number 5. Okay, now notice now it starts to look mathematical. Now it starts to look like equations you can use. The so we're um it's just another version of the same idea, which is that, form number 1, the laws of physics are the same in all unaccelerated perspectives, or are the same at all constant velocities, however you want to say it. And what that meant to us, form number 2, and you want to know these forms, that means no experiment can ever be done to detect the absolute velocity of a single object, right? Then form number 3, that means if no experiment can be done because the laws are always the same, then form number 3 was, okay, then every single velocity is just a relation between two objects, never a property of one. It's all a comparison. And any basis of comparison is legitimate as long as it's an unaccelerated basis of comparison. Then form number 4, which is what started really driving all this two-dimensional stuff that we're doing and that you watched videos about. Form number 4 was that every two-dimensional experiment is really two one-dimensional experiments happening simultaneously yet independently, right? Because we're saying again, like the laws of physics are apply to the x-axis, the laws of physics apply to the y-axis. So any two-dimensional problem is just an x-axis situation and a y-axis situation happening at the same time. Now, I'm going to say, and then you watched a video, then you did lab 3. I mean, I'm going out of order. You did lab 3 and you watched a video about vectors, and you had to do this on your own, but you learned from lab 3, in effect, and specifically from the video that you watched last week, you learned how to deal with two dimensions at once. And the whole, with these arrows that we put together and we added in the last video, the whole trick, the whole technique behind those arrows, those vectors, is that we are saying any two-dimensional quantity can be represented by an arrow, of a certain length and a certain direction, pointing in two dimensions at once, and that the way to relate that arrow to any other arrows is to break down the arrow into an X piece and a Y piece, and do the same thing to the other arrow, and then just relate all X pieces to each other and independently relate all Y pieces to each other. Like the business that I was doing in the video that you watched that you asked me questions about, I was adding displacement vectors, and that's a technique, and it's using right triangles, Pythagorean theorem, SOHCAHTOA, all that. The whole concept of it is we're saying whenever you get what looks like to be a two-dimensional quantity, first just break it down into two one-dimensional components so that we can just keep doing physics in one dimension at a time. That's what that was all about. That's what the displacement addition of displacement vector video was all about. Now, what I'm here to say is if you get that concept of vectors, it works for any kind of vector quantity, any quantity with magnitude and direction, not just displacements. In other words, I'm saying, okay, if you ever want to relate velocity vectors to each other, which is what's happening in this big problem, the second to last problem in the exam. If ever a bunch of two-dimensional velocities are being related to one another, the first thing to realize is that velocity is a vector. It can be captured with an arrow, just like displacement vectors can be captured with an arrow. And the arrows can be added together in the exact same fashion that the displacement arrows were. Like you can make a picture that puts them tip to tail to see what's going on, and then you take each individual one and break it down into its components and add the components individually. The computational technique for adding vectors is one and the same technique, whether it's displacements, velocities, accelerations, forces, whatever. That's point number one, written right here. Point number two, though, is okay. So I'm going to speak conceptually here. Again, I'm giving you the big picture. I'm going to fill in more details on Friday, but this will also help you if you go back. Is a guide so that you can know what to do to go back to approach that problem on the exam or whatever, or look at the old videos. What I'm saying is this. Um, what I'm saying is this. If I gave you a couple of velocity vectors and said add them, like here's a velocity vector and here's another one, what is their sum? I'm telling you mathematically the way you would do it is exactly the way you added displacement vectors in the video you watched last week. Okay. And I don't think that, and I think most of you can be okay with that. The tricky thing is that's never what the exam problem like looks like. That's never what a physics problems, they don't, they're not expressed that way. What happens is you're usually given a bunch of velocity information as you are in this problem here in the exam, and you're supposed to understand that it's an addition or subtraction problem, and you're supposed to figure out on your own which velocity to add to which to get what. You have to make physical sense out of the problem and know what the velocity numbers mean. So, how do you do that? That's the hard part. In other words, how do you set up the computations and the drawings? Well, the answer is this new form of Galileo's principle of relativity. And the form is this on the first page. I'll write it again. The form, what Galileo says is that all velocities are relationships. All velocities are comparisons between two objects. So from now on, when we're looking at a velocity, we're always from now on, so imagine there's three separate objects, object A, object B, and object C, whatever, arbitrary, and they're all moving in different ways in two dimensions, different speeds, different directions. If I say VAB from now on, first of all, if I put an arrow over the V, that means it's a vector. We're taking into account magnitude, direction, more than one dimension, all of that. But if I say V arrow AB, what I mean is velocity of object A relative to object B. I mean the velocity of A compared to B. What that specifically, and you might want to write this down. We've got 8 minutes. If I say velocity of A relative to B, that specifically means another way of putting that is the velocity of A in the reference frame of B or from the perspective of B. Or put another way, that means if B considers itself to be stationary, if B, it's like a first person video game. If B considers itself to be stationary and watches the world go by it, what does it measure A's velocity to be? And remember, this is the whole thing of relativity. Is like B has no less or more right to do that than does A. The Earth can look at the sun and say the sun is moving past it, or the sun can look at the Earth and say that the Earth is moving past it. So if I say VAB from now on, I mean the velocity of A from the perspective of B, and the order does matter, right? If you're that's what the notation means from now on. Now, what I'm saying is if you really take Galileo seriously, we can think of things in three separate cases now. From now on, then, according to Galileo, according to this way of understanding motion, that it's a relation, not a property, we could do three different cases. The one object case would be if we only are considering one object in the world, object A, like Earth, right? We just have one object, Earth, and we want to know what is Earth doing. How fast and what direction is Earth moving relative to itself? Well, if you understand what I've been trying to say about Galileo from Form 1 to Form 2 to Form 3 to Form, or if you ever played a video game, you know, or if you live normally on planet Earth, you know the velocity of Earth relative to Earth is always necessarily zero. Always. Like that's a triple equal sign, right? Just by the definition, like of how motion works, we're now saying the velocity of if you only have one object, it's not moving at all relative to itself. You need something else to compare motion to, right? So the one object case is that, and this is, if you start looking at this long question that looks intimidating, you'll see some of the questions like literally just ask you, how fast is the boat going relative to itself or something? The answer is zero. But then you get to the second object case, like what, once you have two objects, which now velocity starts meaning something. Well, if you really take this seriously, the velocity of A relative to the of B, one thing I know about it is always necessarily the opposite of the velocity of B relative to A, right? I mean, if the Earth sees the sun going east to west, then the sun sees the Earth going west to east, always. And the whole real point of all this is that they're both correct, right? That's what we're really saying here is velocity is a comparison. Every basis of comparison, as long as it's unaccelerated, is legitimate, is equally correct. There's no absolute answer to velocities, is what we're saying. So one object, if you only have one object, it's not moving at all relative to itself. If you have two objects, okay, now you have motion, but it's necessarily symmetric. What I'm doing to you is the opposite of what you're doing to me, always with velocities. And finally, though, the thing that really matters for this problem, and what I will continue to talk about Friday, but the most interesting and tricky part is if you have three objects, that's where velocity vectors add up and mean something physically. If you have three objects, like A, B, and C, then the velocity of A relative to B plus the velocity of B relative to C will always give you the velocity of A relative to C. Now, this is what, and this tells you which velocities can be added to which to get what in a problem like that exam problem. Now, I only have 3 minutes. I'm just giving you an overview right now, but stay with me for 3 minutes. At some level, this statement that I just wrote may look totally obvious to you. It may look like transitivity or something. Like it looks like a pattern, right? A to B plus B to C equals A to C. And I'm saying that's always true. Whatever A and C are, whatever these objects stand for, it's always true. But it's the nature of how velocities work. And you actually, in other words, what we're saying is you can add velocities together and get something when you do, but you have to choose your frames of reference carefully in order to add velocities together. What this is really saying is imagine that object A is you, object B is a subway train or train of thought or whatever, and object C, say, is the train platform. You know that the velocity of you relative to the train plus the velocity of the train relative to the platform always gives you the velocity of you relative to the platform. That's why you ride subways, right? Because you can stand in a subway and you could sit in a subway and do nothing relative to the subway. But as long as the subway is doing something relative to New York City streets, then you are moving relative to New York City streets. I mean, you know this. 0 plus 5 equals 5. So you get home. What the interesting thing about that is you might think that's because of an engine and all this kind of stuff. No, this is just the nature of velocities. Like it's so deeply true of velocities that even if your velocity isn't zero, it still works. Like you know when you are on an escalator, and some people are just standing on the escalator on the right, but you go on the left and you start walking past them, you know the velocity of you is being added to the velocity of the escalator. The velocity of you relative to the escalator plus the velocity of the escalator relative to the mall gives you your velocity relative to the mall. That's why it's worth walking on an escalator. But right? But now, and I have one more minute, but here's what I'm really saying now is that is so true. And you already know it's true that velocities add like that. But it's so true that it's true even when negative signs are involved. Like if you go up the down escalator, it's still true. The negative signs get incorporated. In other words, direction counts, but it's even true even if you're in two dimensions. That's what's not obvious. And that's what's happening in this problem here. What we're saying is I have like 30 seconds. I'm just like, if the problem says, what's the velocity of it tells you the boat relative to the water and it tells you the water relative to the riverbank. If it's asking you for the boat relative to the riverbank, then what you got to do is add the velocity vector of one to the velocity vector to the other of the water to the riverbank plus the boat to the water will give you boat to riverbank. How do you add those vectors? They're two-dimensional vectors. You break them into components and do the exact same thing we did in the video last week. I'm saying that you take vector techniques and deploy them according to this principle, and that's how you add velocity vectors. The only velocity vectors that can be added, this is the end of class, the only velocity vectors that can be added to each other are velocity vectors from two different perspectives. That's the lesson here. I'll just leave it at that. So, all right, so more on Friday, but that's the oh good. Oh, okay, great. Okay, so I'll leave it at that. So have a very nice day. You're being very patient. See you Friday. If you can't come because of work, watch the video. Okay, see you.
Thank you.
Thank you. Thank you. Cool.
Have a good day.
Nice. Have a great day. Have a great day. Okay, I'm turning up. Have a great day.